Last time we left off on VQVAE, and that's vector quantized autoencoder. And today we will go through the details, how do you implement that, and this vector quantization technique, as you might know, is now behind many popular models. Yeah, there was a lot of attention to DALI model by OpenAI, and they use the similar idea of vector quantization in their model, but the original idea is back from 2017, and it was introduced. The vector quantized autoencoder VQVAE was introduced in this paper, Neural Discrete Representation Learning, by I'm not sure, Wanden Ord or something, Oriol Vinyals and Koray Kovakoglu from DeepMind. I'm not sure if I pronounce any of those names correctly, but yeah, you saw what those are. And actually, these people contributed a lot to the generative models. So the some developments on Pixel CNN are also co-authored by many of these, by some of these guys, and as you will see, there is a lot of connection between these models. So let's briefly go through what the theory and the more or rather intuition behind vector quantization in variational autoencoder is, and then we will look at how you implement it. So the kind of core idea is simple here. We want to represent the latent variable as a quantized discrete code, and the encoder in this case will output let's assume we are talking about just like regular 1D data. We encode 1D data. I mean, like not images, but just some data represented as like a sequence or like vectors, right? And then encoder will output, say, some number n of vectors of dimensionality d, and we will match those vectors to some embeddings, which so we can call this a code book. We have a code book, and we compare the outputs of the decoder with the codes from the code book, and then we take the most similar vector from a code book to feed it to the decoder, and in such way our data point will be represented as a sequence of n such vectors, right? And the latent representation will be just a discrete version of it, which means a sequence of indices into the code book, right? And if we are working with images, as we will do in the examples, this would be like D by D grid or N by N grid of codes, but the idea remains the same. We just want to we start in case of RGB image, we start with a tensor of 3 channels, right? And with dimensions, some height by some width. And we want to compress this image into a smaller kind of image. And in case of RGB, we have 256 possible values. And in this case, this value k here represent a number of possible values we can have in a code. Okay, so let's look at how it would be like in this representation.
Sorry, when you say in the code, you mean as output of the code book?
So the code book here is basically embedding, right? A lookup table, and it has k vectors in it. Like so, and the code we have, so the latent representation of an image will be a grid with those values which are bounded by this k number, right? So we kind of represent the image as like for each of these numbers or for each of the of these vectors outputted from the decoder, we take the most similar vector from a code book, and we just so we can select its index, and then we represent. So our latent code would be this grid of indices into the code book, and that would be what we will input to the decoder, right? So here, this like violet color represents the codes from our code book or lookup table, which is our embedding space, and this z q of z given x is just our like latent code, which is discrete, right? So we have each value here represents a number, like an integer, which is an index of the vector in this lookup table, index into this lookup table to represent the image. So in such way, we transfer from like continuous output from the encoder, and we represent it as a discrete or discretized space, which is limited by this code book we have here. Okay, so does it make sense? Is it clear what's going on here, or should I maybe try to explain it better? Yeah, so in this case, yeah, sure, go on.
I guess they explain later how they get the values in the code book. Basically, what you're saying is the blue values down below are indices into the embedding matrix, and the indices are chosen such that the values of the values in the embedding are closest to the output of the encoder.
Yeah. And we
by some metric. So I guess that metric is what we will learn then. Yeah.
So and these embeddings are learned during the process, as well as weights of the decoder or encoder and decoder, and we will see that there are actually multiple ways you can do that. Learn this jointly, and yeah, so it's really, yeah, we will get to that. And interestingly, they present like one way to do it in this first paper, and they kind of say that there might be a better way. And in the next paper, which actually made this VQVAE model so kind of more popular, they use this other method. And in the implementation, we will also have a look of on how that differs, and yeah, and why one might be better than the other. Okay, so now let's look at the objective, and hopefully this will explain of like what's going on here. So the first component here is log p of x given the q of x. So this is just our reconstruction loss, right? So this is a probability of x given latent representation obtained from the x, right? Reconstruction loss. And here we have, here we have two other components. So this SG function is just a stop gradient. And let's look at what we have here. So we have here a loss component, which is like a squared norm of the, or a square of the L2 norm of the difference between the output of the encoder and the code representation, plus some coefficient beta constant, and like the same, but this time we stop gradient with respect to the encodings. And what do these two terms do for us? So this term, it is responsible for learning the code book. So we want our code book to contain vectors which are close to the outputs of the encoder, right? And this is actually what will move at each training step. We will move the embeddings in this lookup table towards the outputs of the encoder, right? And the second term is something that is called commitment cost, and it basically moves the output of the, or makes sure that outputs of the encoder are close to the codes we have in our code book. And this term is here to make sure that the outputs of the encoder do not grow like arbitrarily, because yeah, you can see that if we remove this term here, that then like our outputs of the encoder and consequentially the codes are unbounded. And in this way, we kind of tie it to be like we have these two terms that like act as follows. We want the codes or embeddings to be close to what encoder outputs, but also we want the encoder outputs to be close to what we have in the code book. Okay, and yeah, so that's actually what we have here for the training objective. And like a side note here, which is not particularly important from the like implementation and training perspective, but more relevant to the from understanding perspective, that you can see that the KL divergence term is missing here in the objective, and that is because in this case we assume a uniform prior over this embeddings, and the KL term, like as I stated here, since we assume a uniform prior over Z, the KL term that usually appears in the elbow is constant with respect to the encoder parameters and can thus be ignored for training. And I think that is mentioned somewhere around here, or maybe in some other places, that yeah, your KL term will be just a logarithm of K, which is a size of a code book. Okay, so that's what we do, and then you might ask, how do we sample from this model once it is trained?
One question, Arto, is there a simple implementation of this top gradient concept, or what that is?
Yeah, we will, once we get to the code, we will look what stop gradient is. And yeah, basically here, stop gradient function is, for example, in PyTorch language, it will be just ze.detach, right? And in TensorFlow, it will be like tf.stopGradient of ze. So that's just, we detach it from the computation graph so that the gradients from this like component of the loss function are not backpropagated to the encoder in this case, and gradients from this term are not backpropagated to the code book, to the encodings, the embedded matrix we have here. So that's kind of simple, really. And yeah, we will see it in the implementation, and that will become kind of crystal clear. And there is another thing that basically this kind of operation here, like when we go through the discretization, it's not differentiable. And what we do here, like in terms of backpropagation, like from this point to this point, we just have a straight, what is called straight through gradient estimator. So the gradient, for example, for this particular outputs of the encoder will be approximated as gradient of this kind of embedding we got here. So, and why it works? Because we take this encoder outputs as the closest embedding here. So these two vectors should be really similar, and we just copy over, like essentially we copy over the gradients from the like a code the gradient associated with the code which ended up in this position. We copy it to the encoder at this position, and yeah, we will also see at what does it mean in like PyTorch language. Okay, and yeah, so about sampling. So to sample from this model, we need to somehow get this Z here, and so we need this discrete code, and the authors, actually what they do, they train another model which they call like a prior model, to an autoregressive model. In this case, it was pixel CNN, to model this distribution over the latent space. So as you remember, we can sample and unconditional samples from pixel CNN, and those are supposed to be very similar to what we expect to have in actual data distribution. And in such way, we can just generate samples and feed them to the decoder here, and get our like hallucinated images, right? And this is a bit different from what we had in like standard variational autoencoder, in a sense that there we could just simply sample from a normal distribution, right, and get the samples. But then we like discuss this idea of modeling the latent representation, modeling prior with autoregressive flow. And you can see the connection here. So once again, we can model a prior with some, so we can use a model to learn our latent distribution and sample from it. And that's what we do in this case. And yeah, so they present quite nice results. For I guess this was like good for the time, but yeah, it's hard to really, you know, evaluate it like directly, because we don't have here any like a reference, so something to compare with. And again, this images with like plotted in a small sizes, they look a bit better than if you plot it in larger sizes. But yeah, the results are quite good, and yeah, arguably much less blurry compared to what we had with regular variational autoencoder. And also this approach can be applied not only to images, and in this paper they demonstrated how you can learn like sound with a similar way. And in case of like for audio signals, they modeled the latent distribution with WaveNet. So that's another autoregressive model we also discussed in lecture 1, I believe, or lecture 2. What was it? Okay, so now let's switch to the implementation and have a look at results. So the main component of this variation VQ VAE is vector quantizer. Here is like my implementation of vector quantizer. So what we get is some latent variable, which is output of the encoder. And then we have here, we have an embedding. So it is just basically a matrix of dimensions k, where k is a size of our code book by d, where d is just a dimension of a latent variable, like d, how large our z is, this vector. And here k is a main data compression characteristic. So yeah, we probably will discuss once we're done with the implementation. We can discuss that in more detail. So we take this output of the decoder, and then we compute the distances between the decoder outputs and the embedding vectors. So these are just like regular L2 distances, right? So or Euclidean distances, right? Here, so we have like z squared minus e squared for each entry of in z and in e, and yeah. So if you so z minus e squared is z squared minus 2z times e plus e squared, and that is it in vector form. Okay, then we obtain our code by just doing the argmin over the distances. So for each value in z, we will get an index of the closest embedding. So that is how it works. This distances matrix will be the dimensionality of z by k, essentially, which is a dimensionality of e here, and each element of like once we do this argmin, we have a value between 0 and k, and which represents the index of the closest code in the code book here. All right, and then we just obtain our, here what I call ZQ is just an input to the encoder. So this will be an input to the decoder, sorry, and we just do the embedding lookup into the code book using these indices here. Okay, and so the permutation here are done to make sure that you know, in PyTorch we like expect to have the input to the convolution of shape like batch size by channels, by height and width, and here we want to like when we compute the distances, we basically compute the vector product over the channel dimension in this case, and that's why we need to do these permutations, but that is not really important here. Okay, and then we compute two components of the loss, which we will use to learn. So this thing I call here Q latent loss is what will be used to learn to update the embeddings we have here, and the other, this E latent loss is kind of our commitment cost component. Okay, and that is it. After we then feed the resultant value. Oh, okay, and the final idea here. So to implement this straight through gradient approximation, so I do it using kind of custom autograd function, and the function here is very simple. It takes two inputs here, z and q, and it returns q, and but during the backward pass, it just propagates the gradient back to the first input here, so to Z, and no gradients are propagated to Q. And yeah, so in this way, we will just redirect the gradients associated with this ZQ value here to the output of the encoder we had here. So, okay, I hope that, and yeah, I think that is kind of like really straightforward way to implement it, and it directly represents what we have in like, yeah, at least how I understand it. And there is another way to implement it, which is conceptually the same, but a bit different in how you kind of write it. Let me find it. That's what they do in the, yeah, that's what they do in the original implementation, and that is probably because of the original implementation is in TensorFlow, and there are some differences in, you know, how the autograd works and stuff like that. But and then there's guys who did the reference implementation for the homeworks, just replicated the TensorFlow implementation here. So we take the quantized minus Z, we detach it and add Z. And you can see here that we add and subtract Z, and we have a quantized here. So, but we detach the part of this sum that contains this quantized bit, and the gradient from this operation will only be backpropagated to Z, but because we add and subtract Z, the actual gradients here are just gradients of quantized, right? But we don't backpropagate to quantized because we detach. So yeah, you can probably, this is a bit harder to understand than what I did, but yeah, whatever you see like or feel it to be more intuitive, yeah, these are the same thing essentially. Okay, and we will maybe now look to this other idea, which is presented in the paper and is actually used in the follow-up papers. So instead of learning the embeddings with gradient descent, using this like a second loss component we discussed here, there we can just learn the embeddings to be the exponentially moving averages of the encodings that was the closest ones to those values. Yeah, let's look at probably at the explanation in the paper. Maybe that would be more kind of concise here. So we had this loss component here, but yeah, you can think of it as using k-means of the closest encodings to represent certain entry of the codebook. But because we don't have static encoder, we learn it jointly. Instead of using k-means, we use exponentially moving averages. And yeah, so we will just represent each encoding entry as exponentially a sum of exponentially moving closest encoder outputs divided by the exponentially moving counts for how many like how many vectors fall into this particular or project to this particular entry of the codebook. Yeah, and this method converges faster compared to the gradient descent, to using this loss component. And the benefit of it is independent of the optimizer we use. So it is independent of the optimizer schedule. For example, we might want to decay the schedule for like updating model weights in some particular way, but it does not necessarily we want the same schedule for updating the code book. And here we just disentangle it completely. So the code book is learned not via gradient descent, but just using this exponentially moving averages of the closest encodings. Okay, and let me switch back to the implementation. Okay, so that is an implementation of that idea. So we have like a separate part here where we do the codebook updates. And yeah, so if you want to, yeah, let me know if you want to discuss it further, but essentially that is kind of an alternative way to learn a code book. That's what you need to take.
Question, so there are two parts when we did it the first way, right? Which is you learn the code book, but you also make sure that the encoder produces outputs close to the code book.
Yeah.
So is that part changed, or is that part still remains the same?
Yeah, that part remains exactly the same, and it's still here. You can see in the implementation we still have this E latent loss, how it's called, and yeah, so it will be still like the same value, but the update to the code book is different now.
So yeah, it's only the portion of learning the code book that we changed to the exponentially weighted moving, or not even weighted, just exponentially moving average.
Yeah. So we only changed the way we learn a code book to make it independent of the optimizer updates we have. And yeah, I think that's more like engineering decision here. So yeah, but in my like short experiments, it seems like this really does converge faster compared to like conventional way to do it. And yeah, okay, so the resultant version of once this vector quantizer is implemented, then we have like a regular so the VQVAE will be just obtain the encoding of X, feed it to like quantize it, and get the code and the vector quantized version of our latent, and feed it to the decoder. Then we have the reconstruction of an image. So you can see that this is very similar, but instead of the reparameterization we used in the variational autoencoder, here we use this quantize operation. And yeah, we have a different loss associated with it, but the reconstruction part is essentially the same. And again, you can have whatever encoder and decoder are appropriate for your task here. Okay, and Yeah, so here I will show a quick example with MNIST dataset for this kind of task. So I use a really simple encoder and decoder here. That's like a stack of convolutional layers like we essentially go from the original MNIST image, which is 28 by 28, to a 4 by 4 latent code here. And I use the 16 for the dimension of the latent variable and only 32 like entries to the code book here. And this value k, the size of the code book, it is essentially our kind of data compression bottleneck, right? So we can have only k different latents to represent our image, and this value basically depends on how complex your data is. And for the higher, like more complex data, for which we assume like a higher dimensional, like this underlying data generating manifold or whatever, we shall have a larger value for k. But here we can have like a really small value because that is just MNIST data set. And another kind of dimension, which is which can be thought of independently of the data compression, is the actual size of the code. So in this case, we have a code which is 4 by 4 matrix, just of like it's 4 by 4, and it can have values from 0 to 32 excluded. So and in such a way, we go from like 28 by 28 by 256, which is like the original MNIST representation, right, to 4 by 4 by 32. Okay, and the training is straightforward. We just so here I just do, I think, 10 epochs. Yeah, 10 epochs of training, which takes like about 3 minutes on my laptop, which does not have any powerful GPU. And here are the so the upper row is the source images, and the lower is reconstructions. And you can see that the reconstructions are mostly like really good. Okay, but you can see that this strange 3, I guess it was a 3, is reconstructed to something that probably is closer to 8. And yeah, I think if you search, you can find other like not non-perfect reconstructions. And in this case, like a less good reconstructions are associated with really inputs that are kind of out of distribution. So for example, this something here is reconstructed to not very like nice number, but yeah, it wasn't really nice in the first place, right? And yeah, so here, for example, this 0 has this like discontinuity here, but it is reconstructed into nice closed circle. And yeah, you can kind of get the feeling of how this model kind of extrapolates or interpolates between the data points, however you want to call it.
Yeah, isn't also the benefit of this approach the fact that it will not generate outputs that are off distribution, meaning it will generate outputs which still resemble the inputs if you are in between 2 points, as I recall, right? Meaning that if you're between a 9 and a whatever 8 or 8 and a 3, then as you kind of vary some pixels, it will still adhere closely to being close to a 3 or an 8 rather than going off into some other space.
Yeah, in this case, it is not so easy to kind of vary our as we did like in case of variational underscore, we could took two like latent representation of say 9 and 5, and we could construct the linear interpolation in between those points in the latent space, and we hope that the decoding will be kind of something that is either 9 or 5 or something in between. But in this case, we have, so our each of this image is represented as a discrete code. So we cannot do like this straightforward interpolation in a latent space because we do not have like a continuous structure of a latent space, right? But I think what you are referring to is that essentially our data is represented as a kind of combination of a limited number of vectors which are in our code book, and that is why when decoding each of these like vectors will be like upsampled into something concrete. So for each combination, not for each combination, but we hope that once we sample a latent variable that is in our latent variable distribution, we will get a concrete data point out of it. And that is true, but now the question is, how do we sample a latent variable that is a valid representation of something of actual our kind of something that is in our data distribution. So what we do here, so we construct this data set which contains all the codes produced for our training set, and then we can train an autoregressive model to fit this kind of discrete distribution, right? So the latent code here now can be viewed as a 4x4 image with one channel, right? It is just a 4x4 matrix containing numbers from 0 to 32. And here you can model it as the authors of the original paper did using pixel CNN. But as we are dealing here with just a 4x4 latent, I didn't use a pixel CNN because, you know, there is not so much of this special structure in this just 4x4 like small rectangle. I've used transformer model, but that's just another autoregressive model. And as you remember, we did modeled the MNIST pixel-wise using both pixel CNN and transformer during the homework one, so or in collab one. So I just used transformer because it was more convenient for me. But yeah, the autoregressive model you could also use made. So you can use whatever autoregressive model to model the latent distribution using this data set. Right, so we can have a look and at single data point here in the for example in training codes. So let me just do this. Something oh, okay. Yeah, so it is just some kind of image here you see, and one thing to note here that this pixel intensities do not have any how it's called, cardinal structure. So we don't have 0 is not close to 1 in our case, right? Because we don't have anything in our loss functions that enforces this kind of relationship. So this is just categorical distribution. But what I was thinking, that one can also try to enforce some kind of structure over the latent space, particularly this cardinal relationship to the vectors, and maybe that will result in better samples from the latent distribution. But on the other hand, it might be kind of bad idea because I don't know, I don't think anyone tried it. Yeah, and it is kind of quite easy to do, but I haven't saw some papers presenting that kind of approach. But yeah, maybe I will try it later to see just how it works. Because yeah, because we have this latent variable, this d over latent variable, and maybe we just don't want it to be kind of there is no way to learn a meaningful structure in a linear space, over this latent dimension. But now I'm just wandering off.
So I understand what you're saying is that the embeddings which are 32, they don't have ordering that we would think of in terms of the cardinal order of numbers, right? Because it's just whatever the embedding that's closest, it just matches it. So you could have any kind of distribution of the actual numbers along the embedding indices.
Yeah, and that makes sampling, I believe, a bit harder. So the prior model we have here, it should model this categorical distribution, but it might be easier to model this distribution which have this structure or ordering in it. But on the other hand, it is not clear if we can keep this quality of the expressivity of the model, having this ordering in the embedding space. But if you increase the size, by enforcing some ordering in the embedding space, you can restrict the expressivity of the codes, right? But if you increase the size of the code book while adding this order enforcing loss, then maybe it can both we can still have a good representation of our datum, but also we can kind of get high quality sampling out of it. But that's just kind of speculation, and I haven't tried it yet. And yeah, so to make it work, you need to set it up in a proper way. And yeah, it's kind of probably there are like it's kind of, it may be a difficult engineering problem because you know, we have our encoder and the embeddings we learn are interdependent, and that's kind of restricts the encoder, and we got to yeah, so basically if our latent space does not have any kind of this meaningful ordering ordered representation, then it will be probably really hard to make it work. So yeah, that's just an like random idea. Okay, and let's have a look at the samples. So here I train, I kind of use a small trick. So I train the latent codes conditioned on the class. So this is not just I don't model the codes like arbitrarily, but I model it also given it this class information to the prior model. And the samples we obtain are as follows. And yeah, maybe you can, if we, oh, I don't have it displayed here, but the loss of prior model was still decreasing after whatever I've done, 20 epochs. So probably one can get even better samples where after training it a bit longer, or maybe making this prior model more expressive. We can like change the number of heads in the transformer, change the latent dimension in the transformer representation. I use like a rather small value here. It's only 64, and you know that usually you have something like 512 at least. So, but still you can see that the samples are like quite okay. Most of those are recognizable numbers, but some are just something in between. And probably that was kind of something that, yes, some values in this latent code were not compatible with each other, right? So here it is modeled just as a sequence of integers, and not every sequence of integers will represent the valid number, right? And yeah, we can just do some something fun here. Let's just try to decode the random integers and see what it will be. Yeah, I haven't done it. Just like, let's get, say, how many we have. Sorry. Yeah, sorry for doing it offline, but I think that can be kind of fun. Yeah, that should be right. No, must be tuple of ints, and cannot see what I'm doing wrong here. Yeah, I'm not sure why. Oh, zeros. Yeah, sorry. Okay, now it's correct. And now we just show the decodings. Okay, so you can see that the decodings of random stuff are also kind of random, but also you might notice that there is occasionally something in the center that resembles a number, and also probably the, like, I would assume that there are some codes that represent a blank space, and some codes that represent like our something object here. And when we do this, when we decode these random numbers, then we might have, like here you can see that we have just a line, some kind of line over here, which is completely not representative of the MNIST data set, right? Okay, so now we are done with this MNIST stuff, and let's just have a look at the implementations, reference implementation from homework. Okay, so they use this first formulation of embedding learning objective. They don't use exponentially moving averages, and yeah, but that is not really very important. Even in the paper, they state that we just get a faster convergence, but yeah, essentially it should converge to the same kind of performance, I guess, in terms of reconstructions. All right, and the results are presented here. So you can see that samples are not quite good here, and yeah, but to get as we shall see. Yeah, let's just scroll through it. So the reconstructions are pretty good. So the model is expressive enough, but actually I've tried this street numbers data set, and you can get away with modeling it quite well with a smaller code book. So here they use a code book of, I believe, like, let me double check it. The size of a code book. Oh, okay. Now 128. I think I also used 128 probably, or maybe 64. And you can decrease this D here with no much trouble. And yeah, so this value D is kind of probably should be representative of how complex actually our like the resultant distribution is in comparison to our decoder, right? So we can give more or less information to the decoder to like upsample from, and if we have a more like expressive decoder model, probably we can get away with a smaller dimension of the latent variable. But again, that's kind of speculation on my side. So let's move on. Yeah, and now let's have a look at what they tried here. So the quality of samples are determined by the quality of the prior model, right? And here you can see that the, let's check, the final test loss of prior model was like 2.75. And here they used a simple pixel CNN. It was just a stack of pixel CNN res blocks, I believe. as presented in the paper which actually presented the pixel RNN. And after that, there was gated pixel CNN, and here they try to model the latent distribution with gated pixel CNN. They get a bit better negative log likelihood on the. Oh, it's here. It's even worse. That is okay. So here it's even worse. So the log likelihood they've obtained with gated pixel CNN is worse compared to what they have with the regular pixel CNN, and probably samples are not better. And it's hard to tell judging by this like super small images. So yeah, not much to discuss here. But yeah, what I've observed with this experiments, as I've like made this prior model more expressive, the quality of samples increased. But for the, yeah, I've kind of got cut off here, like in the middle of the way, but I was training this for street numbers data set as well. So here it was again the transformer model, and like before it was kind of very smooth images, and you can see that I'm starting to get some kind of numbers here, but it's still not good enough to produce really nice samples. But yeah, with time, I believe if we put more like effort on this prior modeling, we can get really nice samples here as the reconstructions. I hope I have something start here. Okay, so here you can see the reconstructions from VQ-VAE for this street numbers data set. And you can see that in most cases, the reconstructions are like quite good. And yeah, but in some rare cases, you get it a bit worse, but yeah, most of the time reconstructions are really nice. And yeah, I have compared here. I don't think I have it stored. Okay, so I have compared here the training with exponentially moving averages and with regular approach, and the result were like close, but not quite the same. So yeah.
I do a question, or maybe I'm misremembering, and if so, correct me. But I thought somewhere in the lecture he said like there's also some issue if you continue to increase the complexity of your prior, because then it tends to just memorize, and that's not good. Or is that am I remembering it correctly, or is that not the case?
Yeah, I'm not sure because I do not remember it. But like,
because there was some bounding he did on the how much you can, this, I don't know, bounding is the right word, but some trade-off with making increasing the complexity of the prior.
Yeah. Essentially, as I briefly kind of mentioned, there are two dimensions in which the data compression happens. So one dimension is just the downsampling of the original image. So, for example, in this MNIST example, we went from like 28 by 28 to 4 by 4, right? And yeah, I guess you can go even to 2 by 2 quite without much trouble. And another dimension of data, and that is the main kind of compression bottleneck, is the size of a code book. And if you make your code book really large, then you kind of can, yeah, let's imagine the most as the extreme case of it. If your code book is as large as your training set, then you can just basically have a single entry in the code book corresponding to each data point, and your encoder will have to only, match the data point to the entry in the code book, and decoder should reconstruct the code book entry into the exactly this data point. But in this case, we do not have any data compression, and we so therefore we do not have any generalization, right? And in this sense, you can kind of extrapolate this extreme case. And let's consider another extreme case. If we have only one entry in the code book, and then the best we can do is just learn the mean of all the whole data set, right? And essentially, you want to be somewhere in the right place to model your data distribution, right? And if we, for example, for MNIST, we do not need many codes to represent the numbers. So the numbers consist of a limited number of constituents, lines and semicircles, and you can imagine, like, if we have a code book which has like a proper proper number of lines, semicircles, and circles in it, you can model the MNIST data set quite well. But for more complex data, you will need to have a larger code book. But again, you don't want the code book to be too large, because in that case, we can kind of have an entry for a specific object. And that is not what we want. We want to have entries which can be combined in a meaningful way to represent the data points, but not an entry that represents a single data point, right?
Yeah. So you're saying, for example, if we have instead of it being 32 and 16, if it's 784 and something, then because it's 28 by 28 is 784, then you're pretty much mapping the input space completely. So there's no, at that point, there's nothing latent about it, or you aren't learning anything latent.
Yeah, not quite. So let's think about it. In MNIST dataset, we have 60,000 data points, right? So we have 60,000 examples in a training set. And if we have a code book of 60,000, and the dimensionality of the code will be the same as the dimensionality of the original image, then we can just write each data point into its own entry, right? So it will be just storing the training data set. So that is an extreme case. And you can imagine that if we as we shrink the size of the code book, so the K here, we cannot store each data point individually. So for example, if we shrink it further, we can have an entry for a single entry for one, right? So each one will be stored or not each one, all ones will be stored in one entry of the code book, and then we can have like multiple entries for other numbers and so on. Like in this, I'm talking like in this sense, but yeah, it's not quite that straightforward if you kind of go to the more complex examples, but essentially that is something like to get the intuition of how the size of the code book relates to the complexity of the data, right? Okay, I think that we can, yeah, so I've decided to start a small library to store all the implementation of these models, so that when I might need something like it again, I will not have to re-implement it. And yeah, I want to kind of compress this related information in a nice way to retrieve it in the future. And hopefully, once it's kind of more mature, we can run a bunch of these experiments. And for example, we can check what will happen to the what will happen if we increase the code book by much, you know, and yeah, so probably it will like decrease the generalization capabilities of the model. But yeah, I think we can devise a couple of experiments to play around with it. And yeah, it would be nice to really do it. Okay, let's just go on to the pixel VAE here. So talking about like complexity of the data distribution and the expressivity of the decoder model. So we can have, and yeah, for that, I guess we should, okay, let's not connect. We should go to the collab for this lecture. And in the collab here, they had a bunch of experiments here. So we are using the pixels, a model with pixel CNN decoder, and you can look at the implementation at in the homework solutions, or yeah, so that is one way to implement it. Basically, we use a conditional pixel CNN as a decoder, and it will be conditioned on the latent code we have here. And yeah, I hope everyone remembers how the pixel CNN works and how you can condition it on something. And otherwise, it's just a regular variational autoencoder. So if we do it that way, we will have a nice reconstructions, but the reconstructions will be less dependent on the latent variable. And why is it happening? Because it, as we discussed on that toy example with Gaussians, when we have a decoder that is expressive enough to model our data distribution, it is easier for model to just like set the latent to be as close to standard normal as possible, and use the expressive decoder to model the resultant distribution. And one of possible ways to avoid it is this free bits. It's really very simple, and what we do here, And this was introduced by this inventor of, or co-inventor of variational autoencoder, Dietrich Kinma, I guess, in one of his papers. Let's look, for example, on the implementation here. Yeah, so instead of taking the KL loss as it is, we just take essentially this line takes a minimum, or not minimum but maximum of the KL loss and some constant in this case, which represents a 3 bits. So it can be interpreted as like we can encode information in our latent up to this 3 bits with no cost, right? Because the minimum of KL loss we can have for each kind of entry of the latent is this 3 bits number. And it should be set kind of to some reasonable number. But yeah, actually it can be more complex than just a constant. And in that, if you look at that lossy encoder paper, which I believe is also linked in this homework, let me just find it quickly. So the paper which introduced variational autoencoder with autoregressive flow for latent, they also speak about some modifications you can do to the 3 bits to improve it, but yeah, I don't have much practical experience with that, and I guess the raw version of 3 bits yeah, works as well. Oh, okay, so here they have this soft 3 bits modification. And if you are interested in it, you can try it out, but the original 3 bits works as well as, and is very easy to understand. It is just on like some minimum information you can encode in your latent for free. And with that, we can get maybe something better, but yeah, it's really hard to tell judging from what they have in this collab demo for the lecture. So I don't think they quite made it work. Yeah, not sure. Okay, and another way to like increase the expressivity of a prior is use autoregressive flow or inverse autoregressive flow, and yeah, that they tried that as well, and yeah, once again I cannot tell that it worked really. So I guess that you might see that in this inverse autoregressive flow implementation, it worked better, right? So at least the reconstructions are better than it was before. But yeah, so samples still are not quite good. Yeah, but in the variational VQVAE paper, they mention that the VQVAE actually does not have this problem with posterior collapse, because you know the KL divergence loss is constant in this case. It is independent on the kind of our model, and that is why we can use Pixel CNN as a decoder with VQVAE, probably with more success, but I haven't tried that yet as well. So, but I believe they mentioned it in the paper somewhere. So that is something to try. And also, there is a paper which is called like Pixel VAE, and what they do in that paper, what the authors do in that paper, is a bit more complex compared to what we have in this homework. So they actually use not just use a Pixel VAE or Pixel CNN naively as a decoder, but they have up convolution as decoder, and then they have a couple of layers of Pixel CNN. And you can think of it as like using the Pixel CNN to sharpen the output of the VAE decoder. And yeah, that is another thing to try. But also the results in that paper weren't really good, and like they improved the metrics just by small margin, but on the other hand, you know, the metrics we use here are also not quite representative of the, like they not always match the perceptual quality of the samples, and that is something also like which makes generative models a bit more complicated to evaluate, really. So, during the previous session, I've showed you as mean squared error, which we use for negative log likelihood estimation for these images, how it can fail in some cases when it produced higher numbers for an shifted image, the same image but shifted by one pixel, as compared to just an image which had a part of it simply the mean of the pixels in that part. So yeah, and using the discriminator models to provide better feedback or better loss function is something that you can try to do, and that what we will consider in the generative adversarial network GANs in the next section of the course. Okay, so yeah, enough with it. So VQVAE here, we considered it in the details before, so we can move on. And yeah, you can check out the results they have with it. And again, yeah, the reconstructions are really good, just as well as what I had. And the samples are also quite good, I believe, but yeah, not perfect. But again, you can probably improve it by training a stronger prior model. So okay, and another variant of model which models the latent as a categorical distribution instead of constant or continuous distribution as in VAE is this Gumbel softmax VAE. And we can briefly look at the paper of presenting the Gumbel softmax. So let me just find it. Okay, so here essentially, you can think of this Gumbel softmax trick as a reparameterization trick for continuous or not continuous, or for categorical distributions. And here you can get the idea. So we have some what we called a Gumbel noise, and P sub I is parameters of the distribution outputted by our model. So this is learned, and this is kind of our seed, random seed we get. If you want to relate this to the reparameterization trick done in the original variational autoencoder, so this would be in place of the random samples from the normal distribution, and this will be in place of our means and standard deviations we output from the encoder. And here you can see that the original Gumbel max trick was using argmax here, and a way to make it differentiable is, instead of argmax, we can use softmax with temperature. And yeah, so that is a way to model the distribution, right? So instead of getting instead of sampling, we do this Gumbel softmax, and it provides us with a distribution. And as we increase temperature, the distribution becomes more smooth. And what does it mean for the backpropagation? We get more gradients everywhere, but also you can see if the temperature is high, then our samples are not really close to what we had in actual distribution, not at all like samples from actual distribution here. So that's kind of a parameter to tune when you use this Gumbel softmax trick. Yeah, and that can be used to backpropagate through through sampling from categorical distribution, and therefore we can learn the parameterization pi for a categorical distribution, which we then can use in variational autoencoder. And this Gumbel noise is just a negative logarithm of the uniform noise. And probably there is some really good explanation of why we have this particular combination, but I don't know it. So you can search for the original where the original Gumbel noise was introduced, and why we use this particular value. But yeah, I don't think that's particularly important, but you can see that now we can, once we have that, we can just sample a random variable from uniform distribution, convert it into this G value by taking negative logarithm of it, and just produce the samples as we did with variational autoencoder while sampling from a standard normal distribution as well. Okay. And yeah, so this paper introduced this Gumbel softmax, and the example they show when it can be useful is for variational autoencoder. So they have a section here showing the results for generative modeling for VAE with this random categorical VAE here. Okay. And yeah, so as usually you can kind of use it to model MNIST data set, but you can make anything work on MNIST, so I'm not sure if that's really particularly important what we see here, but yeah, that's another way to deal with categorical distributions as your latent like alternative to vector quantization done in VQ-VAE. Okay, I guess that is the last example. Yeah, you can see that the results are like pretty nice in the demo they have in the lecture for the lectures. And I think that yeah, overall one can argue that the samples from this discrete latent variational autoencoders are better compared to conventional VAEs. But yeah, that's what we have here. And there might be kind of other results. There are a bunch of variations of VAE. So yeah. Yeah, and you can find the implementation of it somewhere in the like yeah, like utility libraries for this course. So there is an implementation of Gumball VAE, but yeah, essentially you can think of it as an alternative for the reparametrization trick for categorical distribution. And you can see that again, you should do some kind of engineering here to make it work. So they have some annealing schedule for the temperature. So probably in the beginning of training, we have like a smoother, like higher temperature, therefore smoother distribution, and the gradients are backpropagating to all the values they come from, kind of we sample from. And as we go further in training, we can have a lower temperature, and yeah, and that will make like the backpropagation kind of more sparse, but the distribution, the samples from the distribution closer to the actual samples. Yeah, the kind of samples from using Gumball softmax, we will be closer to the actual samples as we decrease the temperature. So, and yeah, so they have this parameters here, and you can actually play around with it. So, okay. I think let's just spend the remaining 10 or 15 minutes to discuss. And if you have any questions or comments or want to share some results you've been getting, yeah, please go on. Check the chat. No, nothing in the chat. And yeah, I think I will stop sharing. Okay, so if we don't have anything to discuss here, then I guess we can end the meeting, and I will like post a link in our course channel to the repo I'm working on, and hopefully I will kind of construct some more experiments. Right now it's kind of a bit messy, but I will clean it up and yeah, we try to evaluate different possibilities we have with these models. And yeah,